In this video I would like to discuss different types of number. When discussing any maths, it's important to know the definitions of these different types of numbers. The types of numbers that are important are integers, fractions, terminating decimals, recurring decimals, and surds. Now these types of numbers can be split into two categories, rational and irrational. Let's go through each type of these numbers. So first up we have integers, which are part of the rational group of numbers. This is an important word that will come up time and time again in maths. So an integer is another name for a whole number, whether the number is positive, negative, or 0. Some examples of integers are -3, -2, -1, 0, 1, 2, 3, and so on. A negative integer is a negative whole number. So an example of this would be -5, -11, and so on. Natural numbers are positive integers, such as 5, 10, 43, 120, and so on. So next up are fractions, which are still part of the rational group of numbers. Fractions represent the parts of a whole or collection of objects. A fraction has two parts. We write them as an integer over or divided by another integer. So in this example we have 5 over or divided by 8, and we would say 5/8. So to help us understand this concept a little bit more, let's take an example of a pie. Now if we split this equally into 8 slices, and then someone ate 5 slices, they would have eaten 5/8 of the pie. Or put another way, eaten 5 over 8, so you are left with 3/8 of a pizza, as you only have 3 slices left. The number on top of the line is called the numerator. It tells us how many equal parts of the whole or collection are taken. The number below the line is called the denominator. It shows the total number of equal parts the whole is divided into, or the total number of the same objects in a collection. Let's move on to terminating and recurring decimals. Although they sound similar, they are different, and we need to understand this difference. In simple terms, terminating decimals end where we have an end point of 0 in our division, whereas recurring decimals do not end. They have a pattern that goes on forever, whether it's one digit that repeats or a group of digits that repeat. Let's get into an example of each. First example is 3/8, or 3 divided by 8. In long division it looks like this. So let's try and work through this long division and see where we get to. So how many whole groups of 8 out of 3? We can't do that, so we put a 0 on top, and we want it in decimal form, so let's put it after the whole number and then above it, and now we can put a placeholder 0 here. So now we can say how many whole groups of 8 in 30. We ignore the decimal when we're doing these long divisions here. So that would be 3. So 3 times 8 is 24. We subtract and we get the answer of 6. Now we take one of these placeholder zeros and we can bring it down. So now we get 60. How many whole groups of 8 in 60? That would be 7, because 7 times 8 is 56. So bring that down and we subtract the two numbers, 60 minus 56, which then gives us a 4. We then take another placeholder 0 and bring it down. So now we get 40. So the question here is how many whole groups of 8 are in 40? We would say 5, and 5 times 40 is 40. Subtract the 2 and we get 0. So our final answer is 0.375. Remember, for terminating decimals we're looking for a 0 at the end, which we have. So 3/8 is a terminating decimal. So the next example is 20 over 9. So now when we have this in fractional form, but we want to have it in decimal form, so we will do long division. So that'll be 20 divided by 9. Now let's work through this to get an answer to see if this is repeating or terminating. So first up, how many whole groups of 9 out of 20? We have 2, and we know that 2 times 9 is 18, and we subtract from 20 and we get 2 below. Now we want to use this in decimal form, so we have to put our decimal in front of the 20 and bring it straight up, and then we can start using placeholder zeros to continue our division process. Now in this subtraction part, we're looking for a 0 to tell us when we have a terminating decimal. A repeating number will continue forever and we will see a pattern formed. So 20 divided by 9 is 2, and 2 times 9 is 18, and again we have the same number again, so 20 minus 18, that will give us 2. So we need to continue, so we use another 0, bring it down, and we get back to how many whole groups of 9 in 20, and we know that's 2, and 2 times 9 is 18. Once again we subtract the 2 and we get 2 again, and we do it again now, so we get another placeholder 0, bring it down, and then we get 9s. How many whole groups of 9 in 20? And if you see here, there seems to be a pattern forming, but let's continue and just to confirm. So we know that there's 2 groups of 9 in 20, and then we have 2 times 9 is 18, and we subtract the 2 and we again get back to 2. So now we use another placeholder 0, bring it down, and we get 20 again. So this is a repeating decimal, and when it has a single number repeating, which in this case is a number 2, we can represent this by placing a dot on top of the last digit we have calculated. So the answer here will be 2.2 recurring, and the dot on the final 2 represent that it's the number 2 that's recurring. So other examples of terminating decimals would be 0.4 or 0.75, and other examples of recurring fractions would be 0.3333, and that goes on forever. As we mentioned earlier, we do not want to write 0.333 forever. Since the digit 3 is repeating, we can indicate this by placing a dot above the digit that reoccurs. So that is a number 3, and we have a dot placed above it. Now in some cases, more than one digit can repeat, such as 0.231, 231, 231, and so on. It's the whole 231 part that is recurring. So we can write this as 0.231, and we can place a dot above the 2 and the 1, because 2 is the first number that reoccurs and 1 is the last number that reoccurs. Now there is one final example here, so we can look at this number of 0.5231, 5231, 5231, and so on. It's the 5231 that's reoccurring, so we can rewrite this as 0.5231 and place a dot above the 5 and the 1. So as terminating and reoccurring decimals are examples of rational numbers, we have a rule that we can also rewrite these in fraction form. So for example, 0.4 can be rewritten as 2/5, and 0.75 can be rewritten as 3/4. 0.33 recurring is 1/3, and 0.231 recurring can be written as 231 over 999. Now we move on to irrational numbers. So an example of an irrational number would be something like this: 5.2684, etc. They're more difficult to write as decimals continue forever. They are a random set of numbers going on forever, and they do not repeat, and they cannot be written in fraction form. You're most likely to see these numbers in surds. I'll cover surds in more detail in another video, but in summary, a surd is an expression that includes a square root, cube root, or other root symbol, and we use surds to write irrational numbers precisely, as the decimals of irrational number do not terminate or recur, so they cannot be written exactly in decimal form. So for surds, if we have square roots, to get an irrational number, it would be the square root of a non-square number. So to try and understand this, let's do a few examples. So if we take a first example of the square root of 3, which would give us an answer of 1.73205, and that goes on forever. That is an example of a surd because it's a square root of a non-square number. However, if we do the square root of 16, for example, this would not be a surd, as 16 is a square number, so we can simplify the square root of 16 as 4. So that is not a surd because the decimals do not go on forever. Another example of a surd would be pi, which is an irrational number, which pi we'll cover in another video, but essentially it's the ratio of the circumference of any circle to the diameter of that circle. It's a number that starts at 3.14159.265, etc. It goes on forever and it does not have a pattern to it. So in summary, a rational number is a number which can be written as a fraction where numerator and denominator are integers, any number that has a limited number of decimal places. And an irrational number continues on forever, and we would have to round them if we wanted to write them down. That's all for this video. Hope you found this useful. If you did, please give a like and subscribe, and I will see you in the next video. Thanks.